Hello, welcome to part 3 of the UK Rotary phase converter video series. Really sorry about the delay. I've had some distractions to deal with. I have been seeing all of your messages asking me for further information. It hasn't blown up, I haven't been killed, and I haven't been prosecuted by the electric supply companies. Everything's fine. Let's get into it. The first thing you're going to need to know is the total power requirement of your system. This is so that you can adequately size all of the components and the supply so that you can run this converter and it's actually going to do what you need it to without it all going horribly wrong. So let's look at that now. You need to go around each of the machines that you intend to run off your converter, find the motor data panel plate and get the information that you need from it. The power of the motor is the one that you're interested in, and that may be expressed in either horsepower or kilowatts. This is an old motor, and typically of old motors, the power of the motor is expressed as horsepower, and here you can see it's 1.5. Whilst we're looking at the plate, quick word about the amps. This is important for later on. It says on here the full load amps is 2.3. Refers to the full load amps per phase, so there's 3 wires that go into this motor because it's a 3-phase motor. That's 2.3 amps per phase. Really important to know that you can't just multiply the full load amps by 3 because there's 3 of them to arrive at the total current. It doesn't work that way. There's a load of complicated calculations that we don't need to know about. All you need to know is that what that full load amps is in reference to later on when we start looking at switchgear and fuses and things. It is per phase, also known as the line amps. This is the electrical plate on my lathe. This is on the front of the machine. You might find it near the switch or on the back of the machine. This is not the plate on the motor. This covers the entire machine because of course the lathe has a drive motor and a coolant pump. You can see on here again it's quoting the power as horsepower, not as kilowatts. This machine has a 2-speed motor, as you've seen in part 1. So the horsepower is marked as 4 and 2 because on the high speed of the 2-speed motor the horsepower is double. Don't worry about the 2, just take down the higher value of the 2 numbers. Whatever you do, don't get tied up with trying to calculate power of a 3-phase circuit. It's far more complicated than you can possibly imagine. I can't do it, and it's unnecessary. Just take the power of the motors that you've added up, arrive at a kilowatt figure if your power is in horsepower, and work with that. The beginnings of the magic list doesn't need much explanation. Each of my machines down there, all of my machines are rated as horsepower rather than kilowatts. And there they are. Horsepower is not what we need to know. We need to know the wattage rating. 1 horsepower is 750 watts or 0.75 kilowatt. That's an easy bit of maths to do, which gives these figures as kilowatts. If your motors are already rated in kilowatts, it's happy days. You've got the numbers you need straight away. Kilowatts is a universal measurement of power. A 1 kilowatt electric motor is the same as a 1 kilowatt hydraulic pump or a 1 kilowatt water turbine or a 1 kilowatt engine. It is the same unit of power. So kilowatts applies whether, as a power reading for what we need, it applies whether or not it is a single phase or a 3-phase. It applies universally. This is very helpful. These aren't quite the figures we need, but we're nearly there. Bit of school maths, the power triangle. So power in watts equals volts times amps. So easy. So we know the power, we've got the kilowatts, and we know the voltage because we're going to be running off a single phase 240 volt supply. The one we don't know is the amps. So if we take the power in watts and divide it by the volts, it will give us the amps. That's the figure we need. So there are all the currents of my machines, and these are the currents that they will consume at the point of supply at single phase when on full load. If you were to add all of these up, it's going to make a large amount of current, approaching 40 amps. Am I going to be running all of my machines on full power all at the same time? No, I've only got one pair of hands, there's only one of me, it's a home workshop. So I'm going to take 3 machines. Say I'm not going to be working more than 3 at any one time. So my lathe, very commonly used machine, but let's throw that in. Let's throw the mill in. and say I'm cutting something off on the hacksaw at the same time, I wouldn't dare run the shaper unattended. So we'll say lathe, mill and the hacksaw. That pretty much covers it, doesn't it? Let's add those up. That gives us nearly 27 amps. You'll see how forgiving this system is, because I haven't based any of my converter around a current factor that high, and not once have I blown the 20 amp circuit breaker that I've got in there. I've based my system around an input current of 20 amps. That's what I'm working from. Another good rule of thumb to arrive at your single phase amps as an alternative to the power triangle: every 1 kilowatt of motor power is 4.5 amps at single phase point of supply. None of this is going to work without a power supply. Do excuse the wobbliness, I'm stood on a ladder. This is the consumer unit in my workshop. You will see that your regular circuit breakers you've got, that you get with one of these, I haven't got many regular ones in here, stuff it, but the regular ones you'll typically find and in your house are B rated. This relates to the sensitivity of the breaker and how much stick it'll take before it trips. So it's a B 6 amp. 6 amp refers to the breaking current, of course, but everything has a current surge when it starts up, even light bulbs. So a B rated breaker, you don't have to give it much more than 6 amps for not a very long time before it trips. Not really suitable to run a phase converter off. You'll see that the breaker on my phase converter is a C rated breaker. It's rated at 20 amps, but the C designation means that it will take a higher starting surge of current before it gives up, and it will take quite a lot in excess of that, and you need it. There's also such a thing as a D rated breaker. They'll take even more stick. So this is the circuit board, the distribution box in the workshop. This is clearly fed from elsewhere, namely the distribution board in my house. You'll need something of a similar value at the other end. There's no point having a C breaker at this end if you've only got a B breaker at the other end. And it goes without saying that you're going to need a pretty hefty cable. Cable sizing is something I'm not going to cover in here, but essentially the longer the cable you have, the thicker it needs to be to get the same current down it. My local electrical supplier is City Electrical, and they were quite helpful in advising me what size cable I needed. This is a 16 square millimeter cable to run this lot off. Going back to some earlier drawings, this is the rotary converter. This is the motor that you now need to source to build your converter with. This is the drawing of it in the run position. So this full load 20 amps that's coming down our single phase supply is going to be going down one phase leg to neutral and back out. So it follows that that phase leg needs to handle 20 amps. This is why you need a big motor. You see on my power hacksaw it's only like 2 and a bit amps, isn't it? This is a big motor. Unfortunately, motors are rated by their power rating, not by the line amps, which is the current per phase. So you're going to have to do a bit of detective work. Detective work, I've done a Google search for current rating of 3-phase motors. Found a pretty helpful site, R&M Electrical. UK based site, that's important because in the US the currents are going to be different. Got one here, easy to make a mistake. This is a single phase motor, so you don't want that. 3-phase motors, I've no idea why they've got these different voltages in, but the motor that we're going to typically find is a 415 volt AC motor, which is down this column. So we just go down and down and down until we find something that's about right. Oh look, there's 20 amps. This is the line current, and it says it's a 13.5 horsepower motor or 10 kilowatts. It's always better to go bigger than smaller. And in terms of the motor sizing, the motor you're going to use as a converter needs to be really about 3 times the size of the largest motor you intend to start from it. Biggest motor I've got is 4 horsepower. 1 force 4, 2 force 8, 3 force 12. Motor I've picked up is a 17.5 horsepower motor. It's just the one I found it was the best fit that I could find at the time. Quick look at the type of motor that you're trying to source for your converter. For reasons I don't fully understand, but I've established it through building quite a few of these now. These older types of motor work far better than the modern types, so what you're looking for is a motor with a smooth casing. It's a bit difficult to see all this because it's inside a housing. So you're looking for a motor with a smooth external casing, and typically the diameter of the motor is approximately equal to the length. These motors are called British Standard Ventilated motors, and you'll see they're obviously externally quite different to the more modern motors like this one here, which has got external fins. This one is a totally enclosed fan-cooled motor, also known as a TEFC motor, totally enclosed fan-cooled. What's important when you select a motor, do excuse this bird's nest of wires. I still haven't tidied it up, it's very naughty of me. But inside you're looking for a motor. This is switched off, by the way, you're not about to see me blow up. Inside the motor you're looking for a motor with 6 terminals, so there's 3 there, and there's another 3 there which are joined together with a bus bar because this motor's wide in start, more on that later. If the motor has only 3 terminals, it's no good for use as a converter. All of these motors are pretty old now, and you might find that you've got one with an insulation failure and it trips your earth leakage when you switch it on. From these 6 terminals, see these 3 wires here, these are called the motor tails, and these go to the actual coil of windings on the motor. There's 3 on that side, another 3 on that side. These motor tails on old motors are typically cotton insulated. The insulation gets damp, it fails, it breaks down, and this is very often the only cause of insulation failure. I've got a separate video on YouTube that shows you how to change these tails should you find a motor that's got an insulation breakdown. The best explanation I've been given as to why these motors make better converters than the modern type of motor is that these are made to less demanding standards, are slightly less efficient as electric motors, but that means that they're more tolerant of the kind of magic that we're going to throw their way to, instead of use this as a motor, run it as a phase converter. In the various converters I've tried to build, it's always these types of motor, the very old ones, that work most successfully. They run sweetly, they don't make a horrible humming or buzzing noise. Machines that they run more sweetly. You'll hear that when you start experimenting with your capacitors later on. The motor runs nice and quiet instead of making a horrible humming and buzzing noise. Whilst we're looking at the motor, you'll see I've got an insulating terminal here. So this cable is the one that's coming in. There's 240 volts coming in here, and this is the 3-phase going out to my workshop. Having pulled the gland away, you can see that the armouring on the cable, which is attached to the gland, this would normally form part of the earth, but I've screwed it into an insulating block. This means that the earth supply which goes back to the earth rod in my house, the earth continuity stops at this point and does not go any further. I'm not entirely sure of the electrical law regarding this, because electrical law doesn't cover people making phase converters, but the rationale behind it is that up until this point there's only 240 volts. If anything goes wrong up until this point, it's only 240 that goes back to the house earth rod at the point of my supply. However, the motor is earthed. I've got a separate earth bond on here which I've tested with a meter to make sure it's all happily joined up, and this goes to a separate earth spike. So from this point on, where we've got the 3-phase and the 415 volts between phases, if anything goes wrong with either this converter or any of the machines it's running, the earth current does not go back to my house supply. It goes down this earth cable into a separate earth rod, so there can be no interference or dodgy voltages or anything like that going back into the house. Again, that's my rationale on the matter. Other electricians may say that there are better ways of dealing with this, but this seems the safest way to me. It's not that easy to find these old electric motors. There's not many of them around now. Most of them have been scrapped off. But here's some clues as to where you might go. There's some potential sources down on the left. And if you're looking online on eBay or anywhere, you'll find that people use all sorts of weird and wonderful ways to describe them. There's some clues and combinations of the above. Good luck. So another item you're going to need. I've done a Google search for generator changeover switch. This is the switch that goes from start to run on your converter. So it's a center off switch. And again, the magical current figure which I'm looking at, mine's 20 amps. Just see in the corner of the screen, this is actually a 63 amp switch. But that's according to your installation. So you want a generator changeover switch. In electrical terminology, this is a double pole. All you need is a double pole, double throw, center off. When you start looking at generator changeover switches, there's a lot of automatic ones on the market. Don't go there, you don't need it, it'll cause you a load of trouble in fact. Go for a manual switch. This is just one you turn yourself by hand. You do not need, or you don't want an automatic one. You're also going to need an isolator switch for your converter. You don't want to be leaving it on when you're not using it. Anything like this will do. It needs to be a double pole switch rated for the current that your system requires. These big converter motors can't be started using capacitors like some of the smaller converters do. It's just much easier to spin the converter motor up with a cheap single phase motor. This one is, I think, 1 horsepower. Does me fine. Got it second hand. You can see the foot's broken off there, but it's doing absolutely perfectly. So you need a single phase motor, 1 horsepower, maybe even 3/4 horsepower might do you. You're just going to have to take a guess on what power it needs to spin the converter motor up. As to the speed of the starting motor, you need to avoid a 2-pole motor. That is a 2800 RPM motor. You need to get a 4-pole motor, which typically runs around 14 or 1500 RPM. If you choose the faster one, you'll melt through V-belts very quickly. You're going to have to get a means of momentary operation of the small single-phase motor, which is the starting motor. On my system, I've done this via a little push switch here, which works into a contactor here, single phase, so that's dead easy. The other thing you need is a no-volt release. That's this thing here. And that's operated off the same switch that operates my starting motor. So when the starting motor button is pressed, the no-volt release comes on. The purpose of the no-volt release is, should you momentary interruption in power, it's really important. The no-volt release will break the circuit, it will release. And when the power comes back on, the converter will remain switched off. You do not want the power coming on with the converter in the run position. You'll get a massive current surge. The no-volt release contactor, because it's on the single phase side of the circuit, has a 240 volt holding down coil. You're going to need another similar contactor, this time with a 415 volt coil. This is to allow the capacitors which balance the phases to be brought in and out of circuit as the converter is started and stopped. More on that later. Also, you're going to require some capacitors to help with the smoothing. The exact values for these are really a matter of trial and error. I'll discuss that later in the final section on balancing the converter. Finally, instrumentation. It's really up to you how many instruments you want to put on your converter. You could put an awful lot more on your converter than what I've got here, but perhaps this is to be regarded as a bare minimum. The amp meter in this case is wired to show the total consumption of power at the point of supply from the single phase circuit, which is dead handy because it shows me the performance of the single phase starting motor. You can see the brief surge there as it starts, you can see it coming on load, and as the current drops off, that's telling me that the converter is up to motoring speed. And once it's up to motoring speed, the amp meter is then showing the power consumed by the converter itself, because of course the starting motor has been taken out of circuit. The voltmeter is showing the voltage of the one good phase on the converter. This is the true live that's coming off the supply. You could have several voltmeters to show the voltage on each of the phases. I've just got this one, but I have got the three lights, and they provide some visual indication of the state of the other phases. I've seen some converters with a voltmeter for each phase and an amp meter for each phase too. It's really down to how much you want, but you do need something, and this is probably a good bare minimum. This is all taking far longer to explain than I was expecting. I never thought it would be this long. Apologies if you're finding me verbose. We're going to have to go into part 4, but this video now represents the complete shopping list of parts you need. All of the parts are sized based on your single phase input current. They must all be capable of doing that switch, so I've just put this list up for you. Hope you find this further vid useful. I promise the next one won't take as long as the last one did. And I'll see you for part 4. Bye.